Okay, so the first thing I want to observe is that this problem is a lot like a problem from the Green's theorem section. There in the Green's theorem section, there's a problem that says use Green's theorem and a clever choice of vector field to show that for I've forgotten how it's phrased, but that you can compute area as a line integral around the boundary of x dy. You remember that problem? And so this is very, very similar. Now, how is that going to work? Well, we're looking at the problem says we're looking specifically at flux through the boundary of the region of x dy dz, and I have to remind myself, well, what does this mean in terms of vector field fluxes? Right, this is this coordinate surface integral that it's a little awkward notation, but recall that you can always write such a thing as some vector field dot and then ds. So I'm going to write down our ds vector differential over here, and ds is always the same thing. It's always dy dz, dz dx, dx dy. Right. So what I put in here to make this equal to that? Well, x dy dz, and then there are no dz dx or dx dy terms. Right. So this expression here is equal to flux of this vector field dot ds. So f dot ds. Now how to show that that this is actually equal to volume? Well, we have a flux through a boundary. We're going to apply Gauss's divergence theorem to this vector field, and what that gives you is triple integral over R itself of the divergence of f dv. Conveniently, the divergence of this vector field is 1. Right? The x partial of that is 1 plus 0. So you get that this is triple integral over R of 1 dv, and that's volume. That make sense? Yeah. Okay. Yeah. So I think it'd be a great idea to look back at the section on Green's theorem, find the corresponding problem, and make an analogous argument here to that Green's theorem problem, just to see how, it's really the same strategy, different context. Of course, you're going to be using Green's theorem instead of the Gauss divergence theorem here. But, other than that, and of course, it's going to be a coordinate line integral that's going to turn into a vector line integral instead of a coordinate flux and a coordinate surface integral that here turns into a vector surface integral. Yeah. So the context is different, but the process is morally the same.
Why ds equals to what?
Why ds equals to this?
Yeah.
That's a fact. It's established in the coordinate line integral section. And so there's a whole discussion as to why that is. But ds, of course, is a vector. That vector has components, and what we showed in that section 513, I think it is, in the coordinate line integrals and surface integral section, is that the components of the vector differential happen to be areas of projections into the coordinate planes. So the reason we call this, for example, dx dy, is because the third component of this vector is equal to the area of the projection of that piece of surface into the xy plane. So we just call it dx dy. Yeah, sure. And there's a bunch of details that go into seeing why that's true. Yeah, yes?
So this is the volume projected in the YZ plane?
I'm sorry?
So like this result is the volume computed in...
No, this is just plain old volume. Yeah, that's right. So if in particular, the picture here is we have some sort of a solid that the solid is called R, but it has this boundary surface. That's this surface, right? And this is a coordinate surface integral that's computed over this surface. And the claim is that if you compute this coordinate surface integral over that surface, what comes out is the volume of the solid itself on the inside. And now, so, again, the connection, how is it that a surface integral can compute a three-dimensional volume? Well, the reason why is because we can connect the two and the three-dimensional by way of Gauss's divergence theorem. This is where the magic happens right here, right? Where a flux turns into a triple integral. Yeah. Everybody good? Okay. All right.